Logarithms. Another very tricky skill that will suddenly going to hit you in A-level, and some students will have studied it at GCSE, some might not have done. I think everyone should have done, but I'm always surprised by how few people have studied or understand what logarithms are. So let's start by doing some examples. And I'm hoping these are all quite easy to follow. 10 to the power of 3, otherwise known as 1,000, and 10 to the power of 2 is otherwise known as 100. Okay, 10 to the power of 2 is 10 times 10, it's 100. 10 to the power of 3 is 10 times 10 times 10, so that's 1,000. And if I times those two together, I get 100,000, which is 10 to the power of 5. I could pick a different example. Here's a different example. 10 to the power of 4 times 10 to the power of 3. 10 to the power of 4 is 10,000. 10 times 10 times 10 times 10. 10 to the power of 3 is 1,000. 10 times 10 times 10. And so if I times 10,000 by 1,000, I get 10 million, which is 10 to the power of 7. Now what you'll notice is that, taking the first example, 3 plus 2 is 5. Taking the second example, 4 plus 3 is 7. So a general rule we could say is that 10 to the power of A times 10 to the power of B is going to be 10 to the power of A plus B. Or, more generally, n to the power of A times n to the power of B is equal to n to the power of A plus B. Now, in that last example, n is called the base, and A and B are called the logarithms, or the exponents, or the powers, or the indices, or the orders. But n is called the base. So what about dividing your numbers, your powers? So we've got 10 to the power of 5, which is 10 times 10 times 10 times 10 times 10, so that's 100,000. Divide it by 10 squared, which is 10 times 10, which is 100. So 10,000 divided by 100, try again, 100,000 divided by 100 is 1,000, that's 10 to the power of 3. Do the same thing with the next line, 10 to the power of 4 divided by 10 to the power of 2, that's 10,000 divided by 100, that's 100, that's 10 to the power of 2. And you can see here the general rule, 5 subtract 2 is 3, 4 subtract 2 is 2, and you could do this with any numbers, just test it for yourself. 10 to the power of A divided by 10 to the power of B is 10 to the power of A subtract B. Or more generally, doesn't have to have a base 10, it could be any base. N to the power of A divided by n to the power of B is equal to n to the power of A minus B. Now some people will be saying, no, these aren't logarithms, these are the laws of indices. But it's the same thing. Logarithms are just another way of writing the same thing, writing numbers in a different way. So we could write the same number here, 10 to the power of 2, as 100. What this notation says is that the logarithm, when you've got a base of 10 that is equal to 100, is a logarithm 2. Okay, remember that logarithm is just another name for power. So this function, log, returns the power on that base that is equal to this value. Base 10, the power of 2 is equal to 100. So the logarithm on the base 10 that is equal to 100 is 2. That is the power. And you can see the same thing here. 10 to the power of 3 is 1,000. So the logarithm with the base 10 that is equal to 1,000 is 3. And 5 squared, 25, no problem. So the logarithm on the base 5, that is 25, is equal to 2. And you can see, you know your 5 times table. 5 25s are 125, and so this works as well. So in a general rule, if n is the base, n to the power of x equals y, then log base n of y equals x. Now that is true for any base, but if we use base e is just a number, e is a very, very special number, but it is just a number. E, Euler's number, to the power of x equals y, that's what we call the natural logarithm. The natural logarithm. And so we can use ln, lowercase l, lowercase n, for the natural logarithm. E, by the way, I've just looked it up just because I can never remember it, 2.71828182884 blah 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 46 something something something, doesn't matter. It's one of those transcendental numbers, but it rounds to three significant figures to 2.72. Bit of a weird number, but it appears a lot in mathematics and statistics and physics, so we might as well get used to it. So we can use ln, which is the same thing as log with the base e. Now, inverse functions of logarithms. We briefly looked at this when we did algebra, because we had to know inverse functions. It's how to get from one to the other. Okay, so I've just reminded you of this notation we've just looked at here. So if we want to get x out of the n to the power of x, we do the log base n of n to the power of x, because that will return x as a value. Now you can see that here. 10 to the power of 3, if I want to calculate what the 3 is, I do log base 10 of 10 to the 3, because that will be equal to 3, because 10 to the power of 3 is 1,000. So if we want to get n to the x from a logarithm, this is where it gets weird, we do n to the power of that logarithm, all of that. So raising something to a power is an inverse function to the logarithm of the same base. Bit of a mouthful, bit complicated. Let's have a look at a few sort of examples here. Don't know if this helps you at all. Maybe it does, maybe it doesn't. Log to the base 6n to the log with a base 10 of 10 to the power of 1. That's just log with a base 10 of 10, which is 1. Log with base 10 of 10 to the 2 is going to be log of base 10 of 100, which is 2, which is actually also 2 times log of the base 10 of 10. You can see that from the first line. That's interesting. Hang on a minute, that's interesting. Log with a base 10 of 10 to the power of 2 is the same as 2 times log with the base 10 of 10. Does it work for anything else? Well, let's try it with 100. Log with the base 10 of 100 to the power of 2, that's that number there, which is 4, which is just 2 times 2, which is 2 times, well, the log with the base 10 of 2 was this. So that's interesting. It's almost like we've taken that number 2 and moved it down to the start. Let's do one with a different logarithm. Let's do one with a logarithm 3. Log base 10 of 100 to the power of 3. 100 to the power of 3 is 1,000,000. So that's 6. Well, what is 6? Well, 6 is just 3 times 2. And what's 2? 2 is log with a base 10 of 100. So it's like we've taken that 3 and moved it down here. So a general rule here at the bottom, we could say, if we want to figure out what y is, and we've got log with the base n of x to the y, that's the same thing. It's equivalent to y times log with the base n of x. Does it work with anything else? Well, yes. Do you remember our laws of indices where we were adding logarithms? It works here as well. Okay, so log with a base 10 of 10, that's just 1. Log of a base 10 of 100, that's just 2. And what's 1 plus 2? That's 3. That's log with a base 10 of 1,000. Well, 1,000 is 10 times 100. So log with a base n of a plus log with a base n of b is equal to log with a base n of the product a and b. It has to be. Actually, what we're doing here is just using our laws of indices and writing it in this logarithmic form instead. This is really useful for splitting things up. And here we've got log with the base n of a minus log with the base n of b. And you can convince yourself of this. If the addition is multiplication, then the subtraction is division. This is actually how old slide rules work. You're adding two lengths, but they have logarithmic scales on them. Maybe I'll do a video about slide rules. So here's a summary of everything we've looked at, how to get from x how to get x from n to the power of x, how to get n to the power of x from a log base n of n to the power of x, all the different rules that we've looked at, there it is on one page. So now it's time for you to practice it so you can become proficient. Here we are. Hopefully that QR code will work. Hopefully it will take you to the right page of Isaac Physics questions. If it doesn't, then there are other questions out there that you can find.